I'm Michael Szivos, the founder of SOFTlab, um, and we're a design studio based here in New York City. Most of the work that we do is public artwork, interactive work, stuff for developers, also stuff for clients like IBM for events and things like that. I think one of the things that, I mean, it's not necessarily unique, but what we do, most of the work we do our own design work, but we also produce and install a lot of our work. So a lot of it's done from from beginning to end. So in our studio in the city, we mostly do. We also do a lot of prototypes, a lot of full scale mock-ups and things like that. So what I'll talk to you all about today is just some of our work and how we think about that work, how we produce that work. Also some of the ideas we have towards technology or some of our recent ideas. One thing that I've been more recently interested in is the kind of affinity in disciplines to the kind of overt expression of technology, in particular the mechanical Turk, which is a fake automaton to play chess. So, it's an 18th century device, but in an effort to showcase what technology might be, there's a lot of technology used in order to hide a human chess master in the machine. And so I think this is an interesting condition where while it might be novel, I think most of us would rather just play the chess master. And I think a number of disciplines, including architecture, have had an affinity towards, let's say, the progression of technology, where when we can't actually use the technology, sometimes it gets the best of us and we showcase that technology in a way that is much like the mechanical Turk. So, and this has been happening for years. I mean, one of the famous cases is the curtain wall for the Seagram's building, where because of fireproofing and things like that, Mies chose to put, let's say, smaller and fake W sections on the outside of the beam to express the technology that was at the time fairly innovative, which was hidden inside of the building. So with our work, we try to express a certain degree of honesty with technology, but we also try to push back against that in certain ways. We don't like to overtly express it, or we've learned that over the years. I'd say a younger version of the studio was probably very annoying in that way, that we always tried to showcase the technology that we were using. And that is also to say, like, to not confuse honesty with literalness. This is a project by Alan Wexler, which is called How to Build a Digital Brick Wall. And it's a bit tongue in cheek and satire, where Alan has built a software, I guess, to build a pretty crude brick wall, but he's also made a mouse out of a brick in order to make the brick wall. And Alan is doing this because most of his work is analog and pretty idiosyncratic. And I also love his work, including this project. But I think this is the approach we kind of take about how do we push back against something like this, but also how do we push back the kind of affinity for an overt expression of let's say, technology. As I mentioned, we do a lot of prototyping in the office. We do a lot of discrete modeling. So this is a prototype for a rotating mirror. One of the biggest resources, along with the software we use, the 3D software, et cetera, is the McMaster website. Everything is modeled there. So we often build everything in these kind of digital prototypes, checking tolerances and things like that. And then we build a physical mock-up. And so with our interactive work, I would say there's, I think loosely two types of prototypes. One might be the physical thing. And this is a rotating mirror or a mirror with assembly with a depth camera above it that's scanning this max. And so here's just a prototype of, let's say, the software that would run the installation. So you can see the depth camera is reading on the left, and then it's just getting the center point of that blob. And then you can see the mirror in the middle, with the goal that the final installation is a grid of 10 by 10 mirrors. So this simple software sketch or prototype slowly turns into something like this, which ends up being the interface that runs the whole installation. Which also becomes a tool that we use to show clients how the piece might interact, because it's kind of hard to do that with a lot of the modeling software that we tend to use. But you can see in the middle are the 10 mirrors, and this is just using pseudo points for people. So it's just kind of random noise movement. But within the mirror chambers, or the mirror assembly, which is a sandwich of aluminum and acrylic, there are also programmable LED strips. So the strips are responding to sound. And then the mirrors are basically rotating based on a weighted average of the people in the space. So you can see, and then there's a bit of diagnostics on the left. This is when we're actually installing installation to just check the angles of the mirrors to make sure that they're reading right. And here's the final installation, which again is a grid of 10 by 10 mirrors. And so the mirrors rotate based on the weighted average of the position of people in the space, which are tracked by a grid of depth cameras mounted to the ceiling, and then the lights respond to sound. There's a bit of sound here, but it's just a background track. But you can see, so as I was mentioning before, we didn't, we didn't hide the mechanics of the piece, but we also tried to make them a bit more of the background. So again, like a lot of our projects, we think of them as the kind of experience like an onion skin that you, of course, would see the mirrors and the lights, but people who are interested might take a closer look at the technology that is driving the installation. So we don't hide it, but we also don't express it in any kind of, let's say, exuberant way, or we try not to. Um, and this was for an HP space at a music festival. So, this was also, of course, I would say an Instagram machine inadvertently. But it's a case where we were doing that prototype in the office as a test. It's kind of something we're doing on the side. We didn't have a particular project for it. And then we did it for a proposal for a project in Berlin that we didn't end up getting. And then we ended up making it as a proposal for this project a couple of years later. And from the top, you can really see, they're at a rest state when no one's in the space. And then you can kind of really see that kind of weighted average, which is something we all kind of see if we're using any computational design software. But I think taking that simple idea and then implementing it in something that is physical and built, and doing that in real time. So it's managing all the same kind of numbers and things that we do when we're modeling, but doing it in real time. I'm gonna go to the next slide just for sake of time, but this is a project we did a number of years ago. It's a public art project that we were commissioned for, and it's for a pivot park in Philadelphia. And so there's a much larger development happening on this side, which is like a mixed use education science center. And this park would be like one of the first projects that became an entrance to that area. So we decided to design something that's much more like a gateway piece to that area. And our proposal, or our piece is over here. And it's basically a canopy of woven aluminum elements. It starts off as a series of trunks that then come together and weave together in a kind of idiosyncratic way. At the top, each trunk is a different color or a different gradient of color. And then those get, while it looks like a specific color at the base, they get woven together. And then the goal, without getting too much into the kind of design, is to produce a multi-directional archway instead of the kind of binary threshold that you often see in cities. And so I think these are positions that I find it interesting when we're in terms of design, that we're not looking for a discrete design decision or intuitive one, but we know that we want the canopy to be woven. We know it has its profile shape, so we don't really care the orientation of the pieces as long as they reach that quality of wovenness. So here we're doing like a kind of evolutionary decision making where we're trying to reduce the canopy so it has the least amount of small elements. So it's kind of divide and conquer strategy where it picks one that has the least amount of small elements, and then it makes more iterations in that grouping and then picks another. But what I like, generally, I'm lazy, so that we're not making the design decisions anymore. The optimization is. And so this is one of the details. So it's basically linear powder coated aluminum elements that then have a set of folded brackets. And we assemble this all on site. And so this is the whole canopy, which has about, I think, like 1,500 custom brackets. And those are all laser cut and bent. And so, like, I think many of the projects have been shown before, we're automating the process of the cut file. So we just send this to a metal fabricator. We don't do any of this in our studio. We send this all out, and it arrives on site, and we assemble it. So it's like a kind of large constructor set. Here's some of the pieces going together. Here it is on site. And then this is also a kind of interesting condition. Like, we do make a lot of custom tools. So we're in studio, and even banal problems that we might have, like, I think I walked up and someone had taken the REL catalog and they had cut out all the swatches and they were trying to make the gradient by eye. And most of them looked pretty bad. So we quickly made this tool where we just kind of got the RGB values of all the REL catalog swatches. And then we produce a gradient on the left, and it finds the average. And because of the limitation of the colors, and this had to do with the budget that we couldn't get that many custom colors made, we could check the gradients really fast. And some of them, picking the average, are pretty bad, or it produces duplicate color. So this is something we made on the fly just to develop the coloration of each one of the trunks. And here's the final canopy on site. Here are some of those multi-directional archways or thresholds. And this is another interactive project we did we were hired by Atlantic Rethink. So Atlantic Magazine has a company in-house, like a kind of mini ad agency called Rethink, where they work with a lot of their partners to do non-traditional advertising, as in not magazine ads. And one of their big clients is Lincoln, who is releasing a new car called the Nautilus, or SUV, which had a lot of sensing equipment in it. And they wanted to commission someone to build an installation that used sensors to give visitors a kind of fun experience, and to not frame the sensors around, let's say, avoiding accidents and wrecks and things like that, but how it allows families and people to enjoy the driving experience. So it was cool that we weren't asked to make an image of the car, let's say, or a sculpture like the car. They didn't want it to solely be light-based like a lot of other installations. So what we did is we designed a series of 96 poles that are touch sensitive, and they produce sound. So each one has a speaker, and then there's a LED assembly in each pole. So as people touch it, it produces a tone. It's a bit like a sequencer. Well, it is basically a sequencer in a way. And that's a linear sequencer on the left, a simple version of one. And we developed this kind of radial orientation, like a radial sequencer on the right, which becomes the kind of sketch. So sorry, these are running at the same time. But the idea is that individual people could touch the poles and create a kind of symphony of sound, which in some ways could be melodic, and in some cases idiosyncratic. And you could see when someone touches the pole, the base of it lights up. That says, just like the sequencer, this tone is highlighted, and then it slowly fades. So again, this is the same control for the installation like what I showed previously. And this is what so we had a technical floor. This is what it looks like under the floor. So even though the installation is quite simple, I guess formally, it's basically a headache underneath that floor. And so these are all this is all the wiring and cabling underneath the floor, which is all managed beforehand. This is just a video of installation. So in this case, all the technology is really hidden underneath the floor for obvious reasons, just so people don't trip on it and things like that. And so that's something that we're also interested in, especially with our interactive work, how we create a kind of magical experience where the technology is not at center stage. Although obviously this is something that's driven by technology, but where the first experience is really a kind of magical one. I'm gonna skip through the rest of this video. It's the last project I'll show. And so this is something we've really been interested in lately. Well, in general, I think is like we've done a lot of this work, and like I said, the earlier versions of ourselves, I mean, I don't know for sure, but I think we could have been quite annoying at times, making everything really very much about the laser cutters and the technology we're using. But we've been lucky enough to produce work early on in galleries and spaces where we did have to use everyday objects just because of a matter of budget and resources we had. And we learned from those kind of everyday things that our work resonates with a broader audience when we do things like that, when we're using things other than that technology. So it's something we've been interested in over the years, is how we do a bit of both. So this is a prototype for a project we did in London about, I don't know, maybe 9 years ago for the South Bank Center. And it was 2 hanging installations on each side of the Royal Festival Hall. They have a double height space on each side. But it was the first time, I'm not showing any of that earlier work, but a lot of our earlier work was made of paper and cheap materials. But this was the first time we made something, a form-found structure. A lot of our work are these kind of form-found hanging installations out of aluminum. And while this prototype for that project at the South Bank Center was really exciting for us, and seeing how stiff the aluminum was as we began to put it together, over the years, we've we've thought about ways to push back against this idea of maybe what might be considered the coldness of the production techniques. So this is all laser cut aluminum that's been riveted together. And of course, it's a grid shell, and it has that kind of rationalized order, something you don't find in, let's say, like vernacularly crafted things. And these are just images of the project in the South Bank Center. So this is one of the 2 installations. And this is just looking through the installation, and it's clad with dichroic, or well, a 3M solar film, which is meant to amplify the sun that gets to a solar panel, but also has this kind of dichroic quality where it shifts in coloration as you move around it. And so you can see the grid shell behind it. The aluminum is being clad with that material. And so one thing we're trying to do is to randomize this process, or make this grid shell look woven and less regular. So this is a proposal for a project in San Antonio. It's a new women and children's hospital. It's in the main entrance, the double height space of the main entrance lobby. But this is based on research we were doing in the office for a while, similar to the mirror prototype that we produced a couple of years before that project. And we were thinking about this: how would we randomize this process, or not necessarily randomize it, but make it look more woven or crafted? So our first intuition was to just take a shape and basically, I'm saying throw, but I guess it happened digitally. I don't think it was really throwing things, but throw random lines at this, which is what we typically use for a prototype shape, this kind of cantanoid tube. So throw random lines at this surface. And then again, like we have in the past, automate the kind of production of the cut files. So we did that. And then we had a number of aluminum parts cut. So they're cut into strips instead of X's like the grid shell. You know, they have holes for rivets and things like that. So we made the prototype. These are based on random lines. And we began to put it together, and it looks, I'd say it looks pretty bad from even this view. But when you get up close, it really kind of looks like shit. I mean, you know, there's zip ties, even though this all works within the computer model, you know, there's zip ties that we had to use to hold things together. There are holes that don't line up. And we were really kind of confused. We said, well, how does this not work? And this is, for me, which people in the office now who haven't been around, you know, in those early days, it was really kind of exciting moment, because it was something that we really felt like we were kind of trying to solve a problem, or a difficult problem, which is what I felt like in the early days of the studio, where everything seemed quite new, whereas things are quite iterative now. So in many ways, we didn't know what to think. We didn't know why this was not working. But what we did was we sat down, and again, we could probably read a book about grid shells or form finding or other things like that. But most of our learning comes through things like this, luckily not like catastrophic mistakes. What we thought was, we realized that the grid shell, the points of the grid shell actually do matter at the end of the day. So we took, and we just made a sketch by hand on paper in the conference table. But we thought, what if we keep the points of a quad shape, but then we randomize the X? So here we're just going through random iterations of the X, where we're making out of linear segments and automating it. I mean, and randomizing it, sorry. And so once we came up with that, we said, well, it must be the grid shell, so hopefully that will work. So here's the same prototype if we would have used it, made aluminum strips as a grid shell. And those are the points of that grid shell on the left. And this is the same catenoid shape, the same grid shell, just with the segments of the X's randomized. So it looks like a woven piece, or at least to me it does. You can't see that regularized pattern in the piece, which is what we were originally after. And here again, we sent out to get aluminum parts laser cut. And we're starting to put them together. So here we realize we're on the right track, because it's starting to form the actual shape as we're making it, what the other piece did not. Here's the kind of shadow effect that we were hoping also we would get from the piece. And here too, just prototypes. One on the left, we're just testing the thickness of the strips for the actual project. And here is the piece in the Women Children's Hospital in San Antonio. I'm not going to go too much into this, but here it is on site. And so this was about 3 or 4 years of on and off research in the studio, of also, you know, confronting problems or creating our own problems, which we were quite excited about. solving and the results. Thank you all.